Okay, this is a video that shows you an alternative way to build regression models in R. So in the previous videos, we already discussed using model R package to create a family of models and select our final model from the family. So in R, although there is not a single package like scikit-learn that integrate a lot of algorithms and useful functions, but in general, you can find separate packages in R for the algorithms you see in scikit-learn. And in this video, we're going to give you a simple example of using the embedded LM and polyfunctions to build linear regression models and polynomial regression models based on the car price data from our homework 5. So here is the code. So in this code, we will use this deploy-R package and polycore package. So this is used to compute the correlation matrix. So if your RStudio version is relatively new, you should see a warning message here at the top to let you install the needed packages if they are not installed in your current environment. So for this code, the first we will clean the memories. So this code is just like this button, so it will clean the object from the workspace. And then when you run this code, this line, it will pop up a new window, and you can select the data files that you want to read in, or you can just write another line that specify the paths to your data files. And here I already read my data in, and when you check this, you can see this is the same data set we use in our regression problem from our homework 5. And now we can import our packages, and then we can first do some descriptive statistics. So we can use this summary function. And we can see that we have several categorical columns, and we have several numeric columns. And the first thing we need to do is, we can check the missing values. So here I just build a small chunk of the code to check the empty cells in each column. So after running this, and you can see, we have 18 columns and neither of them contain empty cells. But when you check the data, like for this Levy column, it has some, although there is no empty cells, but there are cells with small dash. So then you may need to think another method. If you want to use this Levy column, you need to use some other method to replace those values or remove those values. Also, when we use the summary functions, we can see for this price column, there is a car that only worth $1, and there is a car that worth 26 million of dollars. So it looks like there are some outliers, and when we check the first quantile and third quantile, you can see 50% of our observations, the car price between 5,000 to 20,000. So I need to. So also we can use some plots to help us to check the outliers, and we can use the histogram or we can use the box plot. And here you can see we have extreme large outliers, and we have several outliers that are close to these to our average values. So here, what I did, I will remove the extreme outliers, but keep those smaller outliers. And I will focus on the car price smaller than 200,000. So for me, I think in the real market that most of the car prices should smaller than 200,000. So then I just create a mask and use it to filter a data set and create a new data frame. So and then we can use the box plot to check the car price in our new date frame. So although it has some outliers, but for me, I think that's okay. And recall that in our statistics, when we use the summary functions, we have some categorical values, and when we want to use to build a linear regression models, we need to change some of the categorical. If we want to use the categorical columns, we need to convert it to factors or numeric values. So first, I will focus on the field type columns. I want to change it to factors. So what I did is, for my new date frame, I will group by, use the group by function, group by field type, and then compute the mean values of the price column. So what you can see, okay, for this field type column, we have 7 unique categorical values, and we have this, for each categorical value we have its mean price. And okay, what I did is, okay, I will use this factor function to convert those categorical values to factors. And here I specify the levels, and based on the mean price, I give the factors an order. So the reason I will do this is by using the functions from this package, this polycore package, I can compute the correlations between my target variable price with the ordered factors. And if you still remember that the factor is like the one-hot encoders in scikit-learn, so it create a new column for each category. A new column behind the scene, it create a new column for each categorical values in that categorical column. And then the second is I want to change the category column into factors. So what I did here is just like what I did for the field type, use the group by function, group by category, and then compute the mean price of the price column. So I think I should run this tool first, and then you can see I have for this category column, I have 11 unique categorical values. For here, I need to mention that, which I didn't talk about in the class, is before you use the encoding method or the encoder, any type of encoders, you can manipulate your data. So for example, in here, I just want to change this category column into factors with 3 levels. So since I have for this column, I have 11 unique categorical values, I will group the sum of them into 3 different classes. So I will group them based on the mean price. Okay, so for the category that the mean price is smaller than 10,000, I will consider it's okay, low price category. And for the mean price greater than 10,000, smaller than 20,000, okay, the median price. And for all the left categories, the high price. And then I will use my class labels to replace the original categorical values in category columns. So here is the code. So the code is really simple, and I will now talk more about this. So after running this, and you can see in my new date frame for this category column, I replaced the original categorical values with my new class labels. So the low price, high price, and the medium price. And then I can use these factors functions, okay, to change the new category column into factors, and also I will specify the orders of the factors from low price, medium price to high price. And then I will change the last. What I did is, okay, I will change the mileage column into numeric values. So when we check this numeric column, when we check the mileage column, we can see it has some numeric part, and also it has the unit that makes this column into categorical values. So we can remove those unit characters, and then use this as numeric function to convert the left part into numeric values. So after converting to numeric values, we can I can use the summary functions to check the numeric values. And what we can find is, okay, there are an observation that a car has a mileage about 20 million kilometers. For me, I think it's hard to imagine that. So I think that could be mistyping or caused by some other reasons. So I will treat this as outliers. And what I did is, okay, I can also use this box plot to help me to check the numeric values. So what I did is, okay, I will consider that the mileage greater than 500,000 kilometers are outliers. So I will replace those outliers with with the exact value 500,000. So after replacing those outliers, we can also run this summary function. Now the statistics looks good to me. And then we can check the correlations. So we will check the correlations between the price columns with the production year, category, fuel type, mileage, cylinders, airbags. So I'll just specify the columns and use this function. So this head correlation. So this is from this polycore package. So when we run this, and we can see, okay, this is the correlation matrix. And now you can see, okay, for the price, it seems, it looks like it doesn't relate it with cylinders and with airbags, but it may relate it with the production year, category, fuel type, or mileage. So, we can build models based on these four columns. So before training our model, we need to split since we only have one single data frame, so we need to split for training set and test set. So I just set a seed to control the random process that to do the splitting. So here I don't have an train set split function in scikit-learn, so I just used the sample function to create a mask to help me to do this splitting. So I will use this mask. Then I will use the masks to filter data. So what I did here is, okay, 80% of the data will be will used for training, and 20%, the left 20% are used for testing. So after having this training set and test set, we will use these LM functions to build linear regression models. So if you are not familiar with these functions, you can see this document that it gives you a general idea about this function. So it's just so in general, this function helps us to feed the linear regression model based on the by default based on the mean squared error. So first, we will use this production year, category, and mileage, these three input variables, to build our model. So for using these LM functions, we need to first specify a formula object. So the price, and then use this mark, and then the production year plus category plus mileage. So this means the price related with these three columns. And then we specify our training data, and then use this LM functions. It will return you a model. So we call this feed one. And then we can create a data frame with a column of our actual values and a column of our predicted values. So first we will specify our input columns, and then here what I did is, okay, we will use this predict function, and we will provide our fitted model, and then we will use in our test dataset, we will choose the input variables, and then use these predict functions to make predict values, and then we have our actual values from our test dataset, and then I use this to build a new data frame. So if we, okay, I didn't run I think I didn't run this one. Okay, should run this one, run this one, run this one. Okay, so if we check this data frame, you can see, okay, we have two columns, the predicted values and the actual values. And then we can manually compute the mean square error. So now you can see the mean square error is about, I think it's about 25 million. So you could think it's a really large values, because in our basketball example, the mean square error is about it's smaller than 20. So the reason is for our target value, for our price, the range is between 0 to 200,000. So you can think like this, even for example, an observation, my predicted value, the distance between my predicted value with the actual value is, if it is 10,000, then its square error will be 100 million. So that's because, but when you think about, okay, 10,000 compared to 200,000, well, it's not that large. So for me, for this problem, I think if I choose this, my car price between 0 to 200,000, then this mean square error, I think it's okay. And also, if you change the car price, if I want to focus on car price from 0 to 15,000, then your mean square error will be, after running this code, just to follow the exact same process I did, you will find that the mean square error is smaller. So you can test this later. I will not show it here. So usually you need to, when you think about the mean squared error, you need to not only consider the modal part, but also you need to think the nature of the your target column. Then I can build another linear regression model. Now this time my price is related with production year, category, mail age, and field type. So then I can compute these. Create a new date frame, and then compute the mean squared error. And now you can see, okay, by adding a new input variable, well, the mean squared error is smaller a little bit. And then we can train a polynomial regression with higher power of the mileage. So if you're not familiar with poly functions, you can check the document. And but in general, what it return is it will return the mileage, the square of the mileage, and so here, since my degree is specified to 3, so it returned the mileage, the square of the mileage, and the mileage to the power of 3. So then, even though it's an polynomial regression, we can still use this LM function, since we already specify each component in this formula. So its input variables will be, okay, production year, category, field type, mail age square, mail age to the power of 3. So since for building the regression we will use the mean squared error, then linear we can use the LM functions to help us build a polynomial regression. And then after training the model, and we can see now this mean squared error became, compared to the second model, the mean squared error became a little bit smaller. But you need to remember the overfitting the part. So the more complex of your model, usually in general, when you use your model in your training data set, you will get a better result. But complex models, usually, if you cross a certain complexity, a certain point of the complexity, then applying your model on the test will be then will become to be worse. So okay, so this is the this video. So I just give you a really simple example that using the embedded function you can use the embedded functions to do the linear regression model and polynomial regression models to handle some regression problems.